Jai Hind. Today we are going to discuss Bayesian belief networks. It is a topic of second unit of machine learning. So what we are going to cover in this lecture is introduction to Bayesian belief networks. Where do we use it? Which concept it uses? The concept is of conditional independence. Then we'll talk about Bayesian network formally. How do we represent it, what it consists of, and a formal definition, followed by the way of inferencing and construction of Bayesian belief networks. The lecture has been prepared from Tom Michel book of machine learning, and the other reference is Artificial Intelligence, a modern approach by Russell and Norwich. So let us start with the concept. What lies behind Bayesian network. So what a point here to be noted is, when we use Bayesian learning, in Bayesian learning we use Bayes theorem. The Bayes theorem is based on the conditional probability. Probability of A when B has happened has been defined with the conditional equation, conditional theorem. What the theorem says? The theorem says that if we have to calculate the probability of A when an event B has already been occurred, that depends on probability of B when A has happened into probability of A divided by probability of B. This is the formula for conditional probability calculation. Here we calculate it as posterior probability. Posterior probability when we are having some experience. Now, when we calculate these Bayesian classification, when we calculate it using Bayesian theorem, sometimes it becomes very complex in terms of calculation, because we have to calculate all the probabilities depending on what is our B. It may be a single event or maybe a collection of an event. So that becomes expensive when we are doing the calculation. One assumption plays an important role here, that is naive Bayes assumption. What naive Bayes assumption says that we can reduce this calculation using the concept of conditional independence. Conditional independence we'll discuss after this slide, of the basic motivation of the reason why Bayesian belief networks have been introduced and what is the background for this. So what the concept is, naive Bayes assumption is used to reduce the expensiveness of the calculation which are used in Bayesian learning when we do Bayesian classification. What the assumption is, it says that all the attributes are independent of each other. So when we are saying that all are independent of each other, then what does it mean? We are putting a too big restriction. So naive Bayes assumption of conditional independence is too restrictive, and if we do not use this condition of conditional independence on all the attributes, then it is really very expensive. It's intractable without such assumption. So there, what we want to release this too much of restriction by using the subset of variables. So here comes Bayesian belief networks, which are also called BayesNet, which are also called Bayesian networks. The Bayesian belief network describe conditional independence among subset of variables. In case of naive Bayes assumption, we are saying that all are independent of each other, all are conditionally independent of each other, all the attributes, whether it is 4, 5, 6. No, here what we are saying, all are not independent, but subset of the variables are independent. It allows combining prior knowledge about independence among variables with observed training data. So whatever existing independence information, prior knowledge we have, that we will use for the calculation of conditional independence, that how much can be which attributes are independent of others. Here what we are using the concept of conditional independence. So Bayesian belief network provides an intermediate approach that is less constraining than the global assumption of conditional independence made by the naive-Bayes classifier, but more tractable than avoiding conditional independence assumption altogether. So when we are having this restriction of conditional independence, if we avoid this, then the Bayesian learning becomes very intractable, very expansive. So now we are avoiding the removing of that conditional independence with help of a subset of variables. In subset of variables, we will find out the conditional independence. It will not totally with all the variables. So let us start with the concept. The first point is, what is conditional independence? So first of all, we should know the definition. What is conditional independence? X is conditionally independent of Y given Z if the probability distribution governing X is independent of the value of Y given the value of Z. What does it mean? It means for all X, Y, Z, probability of X when probability of X is equal to Xi is equal given Y is equal to Yj, Z is equal to Zk is equal to probability of X is equal to Xi given Z is equal to Zk. It means when this is given, Z is equal to Zk is given, then it is independent of what is the value of Y. X is conditionally independent of Y given Z. So when Z value is known, the probability of X for this value is independent of Y. This is conditional independent. What is conditional independence? When we know that Z is assuming this value, then it doesn't matter what value Y is assuming. This is conditional independence. Probability of X is independent of Y given Z. In short, in more compact form, we can write probability of X given Y and Z is equal to probability of X when Z is given. It means the probability of X when Y and Z has happened is equal to probability of X when Z has happened. It means Y is not having any influence on that. X is conditionally independent of Y. It is calculated with help of the Z occurrence, with the occurrence of Z. When Z has already occurred, then probability of X doesn't depend on what Y has been. It is totally independent of that. For example, thunder is conditionally independent of rain given lightning. Okay, so thunder, when rain and lightning is same as when probability of thunder when lightning is there. It is independent, conditionally independent of rain. It is totally dependent on lightning. When lightning has already happened, then probability of thunder can be directly calculated from there. The Y occurrence doesn't influence X when Z is given. When Z is given, this is the condition given. Z is already given. So what is the probability of X? That can be calculated independently of Y. That is conditional independence. Bayesian belief network. This is one view of Bayesian belief network. So what we have in Bayesian belief networks, we are having some nodes, some edges. The edges are directed. Edges are directed. For example, here the edge is from storm to lightning, from lightning to thunder, from lightning to forest fire also. So in this particular example, we are having some variables. The variables are storm, lightning, thunder, forest fire, campfire, bus tour group. These are the variables. What is network? What it represent? The network represent a set of conditional independence. Conditional independence we have discussed on the last slide. So what the network represent? It represent the set of conditional independence. We have already talked about naive Bayes classifier on one of the slides in starting. In naive Bayes classifier, what we assume, all are independent of each other. Here we are having the concept of set of conditional independence. Each node is asserted to be conditionally independent of its non-descendants given its immediate predecessor. So what is given immediate predecessor? It is independent of its non-descendants. So when thunder is there and its predecessor is given, what is its predecessor? Lightning. When lightning is given, then thunder is conditionally independent of forest fire. It is independent of this. So this independence is shown in Bayesian belief networks, which are also called Bayesian networks or BayesNet. What it is directed acyclic graph. There will not be any cycle and it will have directions. The directions are according to cause. Lightning causes thunder. Storm causes lightning. Bus tour group causes campfire. Okay, now what will be given for probabilities in Bayesian belief networks? We will be given a probability table. Formally we will discuss it, what we call it on one of the formal definition slide further. So what we are talking here, that what is given in Bayesian belief network, it is talking about conditional independence. We are having variables. The variables are representing the problem. Those are having some independence, some causal relationship. And when immediate predecessor is given, each node is asserted to be conditionally independent of its non-descendants. What else is given? A probability table is given for each and every node. So if I talk about one node, this one, what it is representing? It is representing a variable campfire. If we see this, the campfire is having two parent nodes. What are the two parent nodes? Storm and bus tour group. So if we denote campfire with C, storm with S and bus tour group with B. Okay, so what the table will present? Each node will have its probability table. So what is the variable here? What is the node? The node is having variable campfire. So C or not of C. It is occurring, or probability of campfire or probability of not of campfire. What is that? Now that is depending on, the value is depending on its predecessors. What are the immediate predecessors? Storm and bus tour group, that we are representing with S and B. So one chance is there, both are true. S is true as well as B is true. One chance is S is true but B is not true. Another chance is S is not true but B is true, and the last is both are not true, both are false. So we are having four combination here. Both the predecessors are true. First is true, second is false. First is false, second is true, or both are false. So for each occurrence we will have the probability associated for camp as campfire as well as not of campfire. C means campfire is true, not of C means campfire is not true. So occurring or not occurring. So each node will have this probability table that will correspond to its predecessors. We have seen this table. What the table is representing, that is for a particular node about its parent node, its predecessors. Now, what concept is the Bayesian belief network represent joint probability distribution over all the variables. In this, we are having variables storm, bus, tour group, forest, fire. How it represents? How does it represent the full joint probability table, probability distribution? That is probability of y1, y2, yn, where my variables are y1, y2, y3, yn is equal to product of. How it is representing the full joint probability distribution table? That is the product of probability of each variable given its parents. Product of probability of each variable given its parent. So, I am having y1, y2, yn, n variables. It will be product of I is 1 to n, probability of yi given parents of yi, where parents of yi denotes the immediate predecessor of yi in the graph. So, the joint distribution is fully defined by graph plus the probability of yi when parents of yi is given. So, what is the joint distribution? That is defined with the graph and with the probabilities of each node given its parent node. A Bayesian network can be used to compute the probability distribution for any subset of network variables given the values or distributions for any subset of the remaining variables. We can calculate probability distribution of any subset of variable given distribution or values for any subset of the remaining variables. This is the capacity, this is the possibility with Bayesian belief networks. So, now let us define a Bayesian network, Bayesian belief network, or we can say BayesNet. So, what is a Bayesian network? It is a simple graphical notation for conditional independence assertions. So, what it is representing? Compact specification of full joint distribution. If we are having full joint distribution, it means we are telling that what is the probability of sum of the variables given all the variables. This we can understand with example of two variables. If I am having one variable x, another variable y, so what full joint distribution will have? When x is true, y is true, the probability. When x is true, y is false, the probability. When x is false, x is false, y is true, the probability. When x is false as well as y is false, what is the probability? So, when we talk about this, in this I am having 4 entries for 2 variables. So, same way I will have 8 entries for 3 variables. I will have 16 entries for 4 variables. Now, that we want to present in a compact form. We are talking about full joint distribution. Okay. So, now what we will do? We will represent that in more compact form using Bayesian networks. What is the concept? We have discussed on previous slides, that it takes into consideration the conditional independence assertions among different variables. So, what is the syntax of Bayesian network? The syntax is, it will have a set of nodes. How many nodes? One for each variable. If we were having x and y 2 variables, then it will have 2 nodes. In our example, previous example, we are having about 6 nodes. So, it is a set of nodes, one for each variable. What else is? It is a directed acyclic graph. There will not be any cycle, it is a cyclic graph. If we start from A, we will not come back to A via different path, via any path. It is acyclic and it is directed, it means we will have some directions like this. It means x influences y. When we are representing edges, directed edges, what does it mean? It means X influences Y. So we talk here about the causal relationship. When we say one directly influences other, it means it causes other. What else is there in syntax? So what we have talked about, for each variable we will have a node, okay, and we will have a directed acyclic graph. Now the third point is a conditional distribution for each node given its parent will be given. What we will have? A conditional distribution for each node given its parent. So that we have already talked about one of the slide, what it is, probability of xi when parents of xi are these, when parents of xi are given. In the simplest case, conditional distribution represented as a CPT, conditional probability table. We said that it is a compact specification of full joint distribution, and we have seen on one of our examples also, that is campfire, not of campfire, bus tour, and other was storm. So we talked about कि for each variable, for each node we will have this particular table. So what this table is? This is CPT, conditional probability table, giving the distribution over xi for each combination of parent values. As we have seen, there were two parent node for that, storm and bus tour. So we took when both are true, when first is true, second is false, when first is false, second is true, and when both are false. So we will see each combination of the parent values, and what will be given, that what we will call that table, that is conditional probability table. So the full joint distribution, full joint probability distribution is represented with help of conditional independence assertions and conditional probability table. Let us differentiate between the two terms. If we consider this particular topology, in this topology we are having one variable weather, other three variables cavity, toothache and catch. Because weather is not influencing any one of these, that is not causing anything. So there is no directed edge. How many variables are there? 4 variables. Nothing is causing weather, and weather is not causing anything else. Okay, so weather is independent of the other variables. Weather is independent of, and when we talk about toothache and catch, when cavity is there, cavity is causing toothache and cavity is also causing catch. So what is conditional independence? When cavity is given, then toothache and catch are conditionally independent of each other. Weather is independent of all other variables, but toothache is conditional independent of catch. It doesn't matter what is happening here, given if cavity is given. The toothache is because of cavity. The toothache is because of cavity. Okay, it is conditionally independent of catch. And what weather is? Weather is independent of all other variables. Toothache and catch are conditionally independent when cavity is given. If cavity is not given, we cannot say both are independent. So these are conditionally independent. We are not saying they are independent. These are conditionally independent. What is condition? Condition is that cavity is already there. If cavity is given, then these are independent of each other. In detail with another example in which we are having variables burglary, earthquake, alarm, John calls and Mary calls. These are our variables: earthquake, alarm, John calls, Mary calls, 5. So what is our example let me say I have installed an alarm to get information about burglary. The alarm will set off when burglary will be there, but it may get set off because of some minor earthquake also. So what we have assumed, burglary is setting off the alarm as well as earthquake is setting up the alarm. So what is the causal relationship? Causal is burglary is affecting alarm and earthquake is affecting alarm. Now what else is there? We are having two neighbors, John and Mary. The textbook from which the example has been taken is already mentioned on content page. That is from Russell and Norwich, Artificial Intelligence, a Modern Approach. So what example says? Example says that the alarm causes Mary to call. It means when alarm will be blown, when alarm will set off, then the neighbors John and Mary will inform the person. Okay, now what else is there? There is a gap also. What is the gap? John may get confused with the ring of phone and may tell that alarm has blown when actually it is not there. It was a ring, a telephone ring. And sometimes what happens? Mary misses the alarm. What does it mean? We have taken to assumption that if alarm is there, then Mary will tell or may miss. And what second assumption we have taken? The second assumption we have taken that John will call in case of alarm as well as sometime with confusion of ring. That alarm is ringing, but actually that is telephone ring. So what is the causal relationship that we have shown here? What is that? Burglary is causing alarm, earthquake is causing alarm, alarm is causing Mary to call, and alarm is causing John to call. So how to represent this network? The topology will be like this. We are having alarm caused from burglary and earthquake. What else we are having? Once alarm is there, then John calls as well as Mary calls. So burglary is causing alarm, minor earthquakes are causing alarm, alarm is causing Mary to call, alarm is causing John to call. What is causing burglary to take place? Nothing. So that is the prior probability. There is no conditional table, CPT table, no parent node. So what is given for burglary? Chances of burglary, that is prior information, probability of B, 0.001. So that is CPT for burglary. There is no parent node, so it will have a single value. Now what about this? What is this? Earthquake. Earthquake is not having any cause. As earthquake is not having any cause, so it will also have a unique value in its table. Now we see what is burglary and earthquake causing. These are causing alarm. So what will be the conditional probability table for alarm? That is probability of A when parents are given. Parent node. What is parent? B and E. What will be there for each combination of parent node? What are the combination of parent node? Burglary has happened as well as earthquake is there. Burglary is there but earthquake is not there. Burglary is not there but earthquake is there when both are not there. So how many entries will be there? If we are having two parent node, we are having 2 to the power 2, that is 4 entries. Now alarm is causing John. So how many parent node are there? Only one. So 2 to the power 1, that is 2 entries. What are those? Alarm is true. Then probability of J when alarm. Second is alarm is not there, false. Same way for Mary calls. So if we see here, how many entries are there? We are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are having 10 entries in our tables. These are our conditional probability tables, CPT. CPT for each variable. So in all the CPTs, how many entries are there? That is 10 entries. So this is the way a Bayesian network is presented, and what it conclude, that depends on the domain. How the domain, what is the domain given, according to that we will decide the variables. So what is CPT? What is benefit of this? What is benefit of this? If we are having when we are having here 5 variables, how many entries we found? That is 10. One for burglary, one for earthquake, 4 for alarm, and 2 each for John calls and Marie calls. And if we talk about a simple full joint distribution, the full joint distribution, how many variables are there? We are having 5 variables. So when we are having 5 variables, what does it mean? It means we will have 2 to the power 5, that is 32 entries. So in full joint distribution, for n variables, we have order of 2 to the power n entries. It grows linearly in order of 2 to the power n. While here we are having only 10 numbers. So that is the compactness of our Bayesian belief networks. This is our Bayesian belief network. The first property is its compactness. 32 entries have been replaced only with 10. If each variable has no more than k parents, then the complete network requires only order of n into 2 to the power k numbers, not more than that. While full joint distribution needed 2 to the power n numbers. So Bayesian belief network is very compact. Semantics. How to calculate it? We have seen on one of our slides that the full joint distribution is defined as the product of local conditional distribution, that is probability of x1 and x2 and xn can be represented with joint with local distribution. Local means predecessor based. So it is product of probability of xi when parent of xi is known, is given. So how do we do it? Let me say I want to calculate the probability of John calls, Mary calls when alarm is there, but neither burglary nor earthquake has taken place. So we can see that if we write the chain rule for this, it will be very lengthy one. But here we will do it with help of local calculation, local conditional distribution. So how this probability will be calculated? It will be calculated with the predecessor, given predecessors. So it will be what we want: John calls, Mary calls when alarm is there, burglary is not there, and earthquake is not there. So what we will take? Probability of J when alarm is there, because J is independent when given its parent node. What is the parent node? Alarm. Same way into probability of Mary when alarm is there. Probability of alarm, what are a parent node for alarm? That is burglary and earthquake. What we want? Burglary is not there as well as earthquake is not there. So probability of A when not of B and not of E, when both are not there, and into probability of not of B and probability of not of E, because these are not having any parent node. These values can be taken from the CPTs associated with each variable, and by multiplication of these 5 values we can calculate the distribution with help of the local probability distributions. So this is the use of Bayesian belief networks. How do we construct it? For constructing Bayesian belief network, we will choose any order of variables, any order. We are given some variables, so we will consider any order. So when we consider any order, what we will do? One by one, we will add each variable to the network. Now what we want? We want the conditional probability table. So what we will do? We will select parents from the other set of elements, remaining set of elements, such that probability of xi when parents of xi are given is equal to probability of xi when x1 is given, x2 is given, it means the full joint distribution. So we will check like that. Now what is important here? When we are taking this, when we are choosing the ordering of variable, that is very important. If we will take it in such a form that one is not causing other, then it will result in a correct one, but not to the most compact. That we can understand with this order. If rather than taking the order of burglary, earthquake, alarm, Mary calls, John calls, if we take reverse, reverse means Mary calls, John calls, alarm, burglary, earthquake, just reverse of that. It is not causal. Mary calling is not causing alarm, but alarm is causing Mary call. So we have taken reverse. So now if when we will add one by one all the variables to the network, then that will not give us the most compact Bayesian network. For example, when I am considering firstly Mary calls, so I created a node for Mary calls. Now what else I am doing? Second, I am taking John calls, so another node will be created. So what will be done now? Now all the links will be created. So if we talk about that John call is independent of Mary call or not, because it will be connected to the remaining what actually already has been added to the network. John calls, before John calls, what has been added to the network? Mary calls. Now will it be connected? Because both are calling because of alarm, but can you ignore this connection? We cannot ignore this connection. We cannot ignore this connection, because when Mary calls, it means alarm is there, alarm was there. Mary may miss the alarm but never calls when alarm is not there. So we cannot ignore this connection. Next is alarm. What is the next variable? That is alarm. Now see, this extra node we got, extra connection we got in comparison to the example, best example we were taking where there were 10 entries. That was very compact, 10 in comparison to 32. But here we have got another connection. Now alarm calls. Is alarm blowing, alarm set is independent of both of these? No. Because both have called. So what are the chances? That influences the chances of alarm. Now burglary. Why alarm has been installed? Alarm has been installed because of burglary. Now if I have to calculate what is the probability of burglary, can I ignore alarm? No, I cannot. Now earthquake. Minor earthquakes are also causing alarm. So can we ignore these two connections? Alarm is caused by burglary. What is probability of earthquake? That also depends on burglary, because earthquake may also have caused alarm. If alarm is there, it means it may be because of minor earthquake. So we have got more connections in comparison to the net that we have, Bayes net that we have discussed here. So what is important? That is the point I want to mention. We need to choose the order very carefully. How should we consider it? We should consider it with help of the causal relationship. What is causing other? That can be taken from domain only. So if we consider this particular example in this order, how many entries we are getting? We are getting 13 numbers. So deciding conditional independence is hard in non-causal directions. So that should be taken care. We should take causal directions. In causal directions, the conditional independence is easy to infer. So here we have talked about construction of Bayesian network, what Bayesian network is, what it represent. When we are creating a Bayesian network, it is creating full joint distribution table with help of local distributions. Those are conditional distribution. So this is all about. Thank you. Jai Hind.